The transit method has become one of the most powerful tools in modern astronomy for studying planets beyond our solar system, allowing scientists to extract extraordinary amounts of information from extremely subtle signals. When a planet passes directly in front of its host star, as seen from a distant observer, it blocks a small fraction of the starlight, causing a temporary and measurable dip in the star's brightness. Although this reduction is often minuscule, it carries within it a wealth of information. A portion of the starlight does not simply disappear, but instead passes through the thin shell of the planet's atmosphere before reaching the observer. During this brief passage, atoms and molecules in the atmosphere absorb light at specific wavelengths, imprinting distinctive spectral signatures onto the star's light. By carefully analyzing these changes with sensitive instruments, astronomers can infer the chemical composition, structure, and even potential habitability of distant worlds. From a cosmic perspective, Earth itself is not an especially conspicuous planet. For an observer far away, aligned precisely with the plane of Earth's orbit around the Sun, our planet would cause the Sun's brightness to dim by only about 0.008% during a transit. This is an extraordinarily small signal, one that pushes the limits of detection even for advanced astronomical instruments. Yet, with a high-quality spectrograph mounted on a space telescope designed specifically for this purpose, even such a tiny dimming could be rich with information. During Earth's transit, the spectral fingerprints of key atmospheric gases would become visible. Oxygen and methane, in particular, stand out because their simultaneous presence in large quantities is difficult to explain without biological activity. These molecules react with each other and would not coexist for long periods unless continuously replenished, making them compelling indicators of life on a planetary scale. Beyond these biological markers, Earth's atmosphere also contains gases that are unmistakably artificial in origin. Compounds such as tetrafluoromethane and trichlorofluoromethane, both members of the chlorofluorocarbon family, are not produced by natural geological or biological processes in significant quantities. Their presence is a direct consequence of industrial activity and technological civilization. From afar, these molecules would serve as technological signatures, advertising not just the existence of life, but the presence of an advanced, industrial society capable of altering its planet's atmosphere in detectable ways. The realization that our own technological byproducts could be observable across interstellar distances forces a profound shift in how we think about planetary observation. Atmospheres are not just records of climate and chemistry, but potential archives of civilization. This idea was explored in greater depth in academic work carried out in the past decade. In 2014, a research project undertaken with an undergraduate student focused specifically on the detectability of industrial pollution in the atmospheres of exoplanets. The study examined whether the spectral features of chlorofluorocarbons would be strong enough to stand out against the background noise of a distant star's light. The conclusion was striking. With sufficiently advanced instruments, the absorption features of these molecules could indeed be detected, provided the observing civilization possessed technology comparable to or more advanced than our own. This result expanded the concept of technosignatures beyond radio signals and megastructures to include something far subtler and arguably more universal: atmospheric chemistry altered by industry. An observer positioned in a particularly advantageous location could, in principle, monitor Earth's atmospheric evolution in real time. Any civilization located along the ecliptic plane of our solar system, the flat disk defined by Earth's orbit around the Sun, would have the opportunity to observe Earth transiting the Sun once every year. Over decades or centuries, such an observer could track changes in atmospheric composition, watching as biological activity intensified, stabilized, or declined, and as industrial pollutants appeared, increased, or perhaps eventually diminished. In this way, Earth would reveal not only the presence of life, but also the trajectory of its technological development. Our planet would not be a static point of light, but a dynamic system, broadcasting its internal processes through subtle variations in starlight. This possibility has important implications for how we interpret unusual objects entering our solar system. If we assume that other technological civilizations might use similar observational techniques, it becomes reasonable to consider that they could deploy probes designed specifically to observe planetary transits. Such probes would not need to land on planets or even communicate actively. They could simply pass through a planetary system, collecting data as they go. The optimal trajectory for such a mission would be one that maximizes the number of observable transits, particularly of potentially habitable planets. A retrograde orbit, moving opposite to the direction of planetary motion and aligned with the ecliptic plane, would be especially effective. This path would allow a probe to linger within the transit viewing zone for extended periods, observing multiple planets as they pass in front of their star. With this framework in mind, the appearance of unusual interstellar objects naturally attracts attention. Objects entering the solar system from interstellar space are rare, and those with trajectories closely aligned to the ecliptic plane are rarer still. One such object, designated 3I/Atlas, has drawn interest because of several anomalous characteristics combined with its orbital geometry. It follows a retrograde path that is aligned to within a few degrees of the ecliptic plane, a configuration that would be highly favorable for transit observations. While the prevailing interpretation is that 3I/Atlas is a comet of natural origin, its trajectory raises intriguing questions about what kinds of observations it could, in principle, carry out during its passage through the inner solar system. If 3I/Atlas were equipped with a spectrograph, it would have had the opportunity to observe transits of multiple inner planets as seen against the disk of the Sun. During its journey, alignments occurred that could have allowed observations of Mars and Mercury transiting the Sun simultaneously, followed by Venus and later Earth. Each of these events would offer a unique window into the atmospheric properties of the planets involved. Venus, with its dense carbon dioxide atmosphere, would present a stark contrast to Earth's biologically altered air, while Mars and Mercury would serve as examples of worlds with thin or negligible atmospheres. Observing all of them in sequence would provide a comprehensive comparative dataset, revealing how different planetary environments manifest in transit spectroscopy. In practice, however, the geometry of the solar system introduces complications. The planets do not orbit exactly within the same plane. Each has a small inclination relative to the ecliptic. These differences, though minor on astronomical scales, can be decisive when it comes to transit observations. From the specific vantage point of 3I/Atlas, most of potential transits were near misses rather than perfect alignments. Only in the case of Venus did the geometry line up precisely enough for an actual transit to be observable. This limitation underscores how delicate and precise the conditions for transit observations can be, even within a single planetary system. Despite these constraints, the broader implications remain significant. The fact that such alignments are possible at all means that Earth and other planets like it are not hidden from cosmic view. Given enough time and enough observers distributed throughout the galaxy, it is statistically plausible that some would be positioned to notice the subtle dimming caused by Earth's transit and to analyze the accompanying spectral signatures. Our atmosphere, shaped by billions of years of biological evolution and centuries of technological activity, could serve as a detectable beacon. Even without intentional signaling, we may already be advertising our presence through the chemical fingerprints we have imprinted on our planet. This perspective invites a deeper reflection on our place in the universe. Traditionally, discussions about the search for extraterrestrial intelligence have focused on whether we can detect others. Transit spectroscopy reverses the question, asking instead how detectable we are. It suggests that civilizations need not broadcast powerful radio signals or build colossal structures to be noticed. Simply by existing and altering their planetary environment, they may leave traces that are observable across interstellar distances. In this sense, the search for life and technology elsewhere is inseparable from the study of planetary atmospheres, both near and far. As our own observational capabilities continue to improve, we are beginning to apply these same techniques to distant worlds. Space telescopes are already probing the atmospheres of exoplanets, searching for water vapor, carbon dioxide, and other key molecules. In the coming decades, instruments may become sensitive enough to detect biosignatures and technosignatures similar to those Earth would display during a transit. When that happens, the ideas explored through thought experiments and theoretical studies will move from speculation to direct observation. The universe may turn out to be filled with planets, quietly revealing their stories through the faintest of signals, waiting for observers patient and precise enough to read them.